Hello, my name is David Timmins. I work at the University of Birmingham and the University of New Brunswick. I'll be talking about the global propagation of ionospheric disturbances associated with the 2022 Tonga Volcanic Eruption. This work is a collaboration between the University of Birmingham, the University of New Brunswick, and the University of Hamburg. I'll start off with a really brief introduction to the event before getting into some of the measurements and modeling that we used to study this event, and then go into the global and regional behavior of the waves propagating out from the eruption. I'll then finish off with a quick characterization of the waves and some hypotheses about the origins of some of these waves. So the Hunga Tonga Hunga Hapai volcanic eruption occurred on January 15th at around 4:15 UT. Here we have a time series of the surface pressure disturbance or pressure anomaly from Wright et al., which I have a lovely paper in Nature now, that shows the surface pressure disturbance associated with this event, where you can see, or about 45 kilometers away from the event center. Where you can see there's a main explosion followed by a number of subsequent eruptions that can span from the original time of the eruption to 6 or 7 hours after the event. This is just some imagery of the actual eruption itself. To study the effects of this eruption on the ionosphere, we used about 4,700 GNSS receivers distributed all around the world, where the black X's here are the locations of GNSS receivers that we'll be using to kind of just get an initial impression of these disturbances. And the blue boxes are localization domains that we use to do a deeper dive into some of the behavior that we're seeing. The red dots obviously are the locations of the GNSS receivers. In addition to GNSS data, we also use a LAM wave simulation called the Transient Inertia Gravity Wave and Rossby Wave Dynamics model, where we've imposed Gaussian perturbation at the location and time of the eruption, superimposed on a barotropic atmosphere, and then defined it based on the LAM wave dispersion relationship given here. We've tuned the depth and other parameters of this disruption to the observed structure of the surface pressure perturbations away from the source. This is just an example of the surface pressure anomaly, or the height anomaly, or atmospheric height anomaly, or thickness anomaly associated with this simulation. See if I can get this to run. Yeah, so you can see the LAM wave propagating out from the source to the perifocal point and then back again. As this pressure, or this LAM wave, is highly non-dispersive, and it generally has only very few dissipation mechanisms, mostly through surface drag, where you can see these, where you have interactions with mountain changes, or chains, the structure of the emitted LAM wave is warped a little bit as surface drag operates on the wave. These waves, as you will have seen in US talk, propagate around the world about 5 times in terms of pressure disturbance, or for 5 days in terms of a pressure disturbance, and were observed in the ionosphere about up to 3 days later, as the Zhang et al. 2022 paper discusses. So, detrending the GNSS data, so taking vertical to electron content or integrated electron density of the ionosphere from these GNSS receivers, removing the general trend and looking at the anomalies, you get the black curves for these various different locations, so New Zealand, Australia, Japan, Eastern North America, South Africa, and then Northern Europe. The red is the modeled surface pressure anomaly from the LAM wave simulation. In general, you can see that there's a pretty good correspondence between the arrival of the surface LAM wave and the arrival of the ionospheric to electron content anomaly. You can also arrange things in terms of distance from the epicenter, from all of the GNSS receivers versus time, and this allows you to kind of get a more global picture of the propagating waves out from this event. And you can really see in general, like we can see these waves even out to 16,000 kilometers plus, and it's, again, as you would have talked about, for several days thereafter. So these waves propagate all the way around the world several times. In the near field, we have these larger scale TIDs that are moving at much faster velocities, anywhere between 600 and 900 meters per second. Then we have subsequent a subsequent front of waves, beginning with the Lamb wave given by the solid black line here, and the dashed black line, which are the positive and negative pressure anomalies. Followed by a number of subsequent gravity waves, either from the initial eruption that are propagating slower than the Lamb wave, or subsequent eruptions thereafter. This is just a video of the propagating waves out from the event over the southern tip of South Africa. And so you'll see fronts of waves propagating towards the perifocal point, where these lines here are icing range markers. So you can see a really clear front of waves propagating over South Africa, originating from this event. Similarly, we can look at the same type of thing for Oceania. Wait a little bit here. This is just some background waves, and then boom, there's our large-scale TIDs followed by subsequent MSTIDs propagating out from the eruption location. So we can look at our localization domains now that we showed before in those blue boxes. And you can see in the near field again we have these LSTIDs moving out from the eruption at speeds between about 600 and 900 meters per second. I'll justify that choice of speed in a few seconds. Followed by a Lamb wave front and then subsequent gravity waves. In Australia, you don't really see much of these LSTIDs, but you do see a clear Lamb wave front followed by those MSTIDs. At Hawaii, interestingly, Hawaii sits at the conjugate point to the eruption itself. So not only do we see LSTIDs at Hawaii that seem to be propagating directly from the eruption, but we also see LSTIDs at Hawaii that occur nearly coincident with the eruption, ahead of the propagating LSTIDs. And these are conjugate waves due to the dynamo-induced electric field from the event. So we have conjugate LSTIDs, then propagating LSTIDs, and then we actually see not much in terms of subsequent or coherent wave activity, likely due to the interference between waves propagating directly from the eruption and conjugate waves being induced over Hawaii. So Hawaii is really going to be an interesting place for people to really look at or diagnose some of the physics that's going on associated with this event. Hawaii, you see a clear Lamb wave front. Eastern North America, you see a clear Lamb wave followed by some gravity waves. And South Africa, it couldn't be clearer. You have this wonderfully clean wave packet, beginning with the Lamb wave and then subsequently thereafter. Northern Europe I won't talk about because it's dynamically quite a bit more complicated, and there was a geomagnetic activity around that time as well. So some things to point out here is we seem to have this large azimuthal asymmetry. We see LSTIDs that are able to propagate very well towards New Zealand and Hawaii, but don't make it to Australia, just slightly to the west. Originally, we thought this might be the result of magnetic field preferential propagation of these LSTIDs, but having a discussion with Sharon Vadas and a few others, we've actually come to a different conclusion about that, and I'll talk about that at the very end of this talk. So of course we want to characterize the phase speeds of these waves. So we did this via two methods. One is just simply taking the crests from those range time plots from before and using the slope to get the phase speed. Another is to do this triangulation method, where we independently use or match features between different waves from different lines of sight, and then triangulate the velocity out from that, or the phase speed from that, making no assumptions about the orientation of propagation. So we don't have to assume that it's all, isotropically propagating from the source with this method. And what we find is largely consistent velocities or phase speeds from both methods, where the first LSTID in the near field, particularly within 2,500 kilometers or 2,300 kilometers, reached speeds as high as 900 meters per second, with subsequent LSTID reaching speeds around 600 meters per second, and both of these generally flatlining out beyond 2,300 kilometers at around 600 meters per second. The subsequent MSTIDs were moving at around 200 meters per second, and that associated with the Lamb wave was pretty close to 300 meters per second, but our uncertainties are rather high. It's very likely that this is directly coincident with the wavefront, or the surface Lamb wave front. So this is my final remark. These are some simulations from HiMCM from Sharon Vadas and Eric Becker, where they show we'll say anomalies in the lower and mid thermosphere associated with the eruption. And ultimately, due to the orientation of the background winds in the upper mesosphere, lower thermosphere, these thermospherically induced perturbations due to the eruption have preferential propagation. So rather than us having these preferential magnetic field propagation of these waves, it's actually far more likely that the LSTIDs that we're seeing in the near field have this, azimuthal asymmetry due to the asymmetry in the thermospheric response, not due to some magnetic field interaction. And so if you watch this simulation, let's see if I can get it to play again. I probably can't. You'd see that these large-scale thermospheric waves propagate over New Zealand, but they actually dissipate before they reach Australia. And so this is largely consistent with the total electron content observations that we saw before. And so we invite you to see a full talk from Sharon at AGU 2022 to get the full picture of what's happening. So finally, I'd just like to say thank you. Obviously, I'm not there in person, and so I can't, field questions directly, but please send me an email at david.timmons@gmail.com. And I'd be very happy to answer any questions that you might have. All of these results, except for Sharon's simulations, can be found in our 2022 GRL paper listed down here. Thank you for your time.